welcome to Chemistry at Honeyga. Today we'll be picking up where we left off with our last discussion, which is dealing with metals and nonmetals and how they gain and lose electrons to become stable and therefore end up forming ions. Now metals, it's easier for them to lose to become stable. Nonmetals, it's easier for them to gain, and by looking at how many they're losing and gaining, we can see exactly what charge is going to form, and that's going to affect its formula as a compound. First step in looking at this is finding out how many valence electrons we've got. So based on where where aluminum is at on the periodic table, it's in the third over in the S&P block. And remember, every column over you are in the S&P, that's how many valence electrons you have. So aluminum has 3 valence electrons. So this would be its electron dot, Al with 3 dots around it. Now at this point, you either gain 5 or lose 3 to become stable. It's easier to lose 3. But those electrons have to go somewhere. Aluminum just can't lose them into the surrounding world unless something is taking them. So if we've got a metal that needs to lose electrons, we need a non-metal that needs to gain electrons. And in this case, we're going to look at aluminum mixing with chlorine. Now, chlorine, based on where it's at on the periodic table, it's in the 7th column over in the S&P block. It's just one away from the noble gases. So chlorine has 7 valence electrons. So you draw a Cl with 7 dots. Now remember, you're stable when you're like your nearest noble gas. If you look at where chlorine is, it can gain 1 to look like argon, or it can lose 7 to look like neon. It's a whole lot easier to gain 1. So when aluminum gets together with chlorine, chlorine is perfectly happy to take electrons from the aluminum. But the thing is, chlorine is only going to take 1, and then it's full. And since Cl is neutral, when Cl picks up an electron, it's going to form Cl with 8 dots. Now it has 8 valence electrons, and because it has an extra electron, it's going to have an overall charge of -1. So what we end up doing when chlorine takes that 1 electron is it's going to become a stable Cl minus anion, and we call that anion chloride, and it's going to have a charge of 1 negative. Now the thing is, aluminum only lost 1. It has 3 electrons it needs to lose. Well, if 1 chlorine came in and took 1, another chlorine can come in and can take another. So fundamentally, what's going to happen is what we're looking for is the mix of these two things so that overall the substance will end up perfectly stable. In other words, everything involved in the reaction, all of the atoms, will gain and lose electrons to become stable. So in the case of aluminum, we only lost 1. Another chlorine comes in, and it can steal a second chlorine, making another chloride anion, and that still leaves 1 electron, so we'll need a third chlorine to come in and take that third one, and forms Cl with, once again, 8 electrons and a 1 negative charge. All of those chlorine ions, called chloride ions, have 8 electrons, so they're all stable as is, and the aluminum lost all 3 of its valence electrons, so it's also stable, and now we've got the Al cation. And since it lost 3 electrons, we don't have any dots left in what used to be its valence level. And its overall charge would then be 3+ because it lost 3 electrons. It's got 3 more protons. And at this point, every single atom involved in the situation has a noble gas electron configuration. So everything ends up stable. So what is the compound formula that forms when aluminum and chlorine gets together to become stable? It's going to be AlCl3. And that's why. That would be what we need for the perfect transfer of electrons for everything to become stable. 1 aluminum and 3 chlorines would make that happen. So aluminum chloride is actually AlCl3. Now, one of the things you need to remember here is what we're really looking at is an equal transfer of electrons. We have to look at how many one needs to lose, and that's how many of the others need to gain, and vice versa. So in this case, aluminum needed to lose 3. Each chlorine would only take 1, so it took chlorines. But overall, the number of electrons lost still equaled the number of electrons gained total on each side. So when those two amounts are equal, then we're going to end up with a stable neutral compound of aluminum chloride. Now, another example would be if we put aluminum with oxygen. So with chlorine, which had 7 valence electrons, when we get together with oxygen, oxygen is in the 6th column over, so it's got 6 valence electrons. So the oxygen doesn't need 1, it needs 2. So the oxygen comes in, it takes those 2 electrons, and that forms, once again, a stable anion of oxygen with a 2 negative charge, but this aluminum still has an electron it needs to leave or to get rid of. So another oxygen comes in, and here's the problem. Once it steals that one electron, while that aluminum is stable, the chlorine only has 7 electrons. So what has to happen is another aluminum comes in. If we have more than one oxygen, we have more than one aluminum as well. Another aluminum comes in and gives that next electron in order for oxygen to become the stable oxide anion, O2 minus. So at this point, that second aluminum still has 2 valence electrons it needs to lose, but the first aluminum ion is stable. That's lost all 3 of those electrons. Now, if another oxygen comes in, it can take those remaining 2 to form another oxide anion. And at this point, both aluminums have lost all of the electrons they need to become stable. So we end up with 2 Al3 plus cations being formed and 3 O2 minus anions being formed. Well, if at this point the electron transfer is equal, the aluminums lost 6, the oxygens gained 6, that means we must have formed a stable compound, and all we have to do is count. So what's the formula for the ionic compound aluminum oxide? It would be Al2O3. With 2 aluminums and 3 oxygens, the transfer of electrons is equal, and everything ends up with the noble gas electron configuration. So that's really what we do when we find the formulas of ionic compounds, is we're looking at that equal transfer of electrons, where in the end, all of the atoms become stable ions. Now, we talked about monatomic ions from the S&P block. If you're on the left, you're going to lose. If you're on the right, you're going to gain. The metals keep their own name. So if you had potassium chloride, the K plus is just still called potassium. But the nonmetals end up changing their last name to IDE. Well, there's other monatomic ions that behave a little bit differently. And I'm not saying they don't lose electrons if they're metal. That still happens. The thing is, some metals can actually form stable charged ions while losing different numbers of electrons. So there's actually 2 stable iron cations, iron 2 plus and iron 3 plus. Copper forms also 2 stable ions, Cu plus and Cu2 plus. There's a number of metals on the periodic table, some of them in the transition metals, some of them over in the lower P block, that will become stable while losing different numbers of electrons. Now, it's not like an infinite number of different possibilities. You'll notice each of these, there was really just 2 different things it could do. But what that means is these types of elements you can't predict just by looking at where they're at on the periodic table. So when we're looking at forming compounds from substances like the transition metals, it makes it a little bit more difficult because you can't just look at how many dots and lose those dots. Because of the d electrons being involved, makes the energies a little bit more complex. Now, first thing we have to do is how do we tell apart the 2 types of iron and the 2 types of copper? Well, what scientists eventually did was they just use Roman numerals to describe exactly what your charge is. So if you've got a metal that can have more than one stable charge, then you literally use Roman numerals and state what the charge is going to be in that case. So Fe2 plus, that would be called iron 3. And that literally means it has a 2 plus charge. I'm sorry, iron 2. I believe I said iron 3. But the second one, Fe3 plus, that would be iron 3. So when we have cations that can have multiple charges, we use Roman numerals to state exactly which one it is. So as long as you can count to 4 in Roman numerals, I, and then IV for 4, you can basically name any of these cations. And really what's going to happen when you see a formula is it will say iron 3. So I know what I'm using is Fe3 plus ions, not Fe2 plus ions. And the one thing about these is even though it on the surface makes it look more complex because we've got options, in the end, it's a little bit easier because they're literally flat out telling us what the charge is with Roman numerals. We don't even need to look it up. We just need to know the Roman numerals. Now, we also can have groups of atoms that have a charge. So we've got our simple monatomics, our more complex transition cations, and then we also have groups of atoms with a charge. And if you look on the back of your periodic table, you'll notice that's where we've listed the common cations and anions that we're going to run into in chemistry. So we've got our names and formulas there. Well, A number of them on the backside are just monatomic substances, single atom cation and anions. But there's also, especially in the anion side, the negatively charged side, there's a bunch of groups of atoms that are stable but have gained or lost electrons. So these are the ones that really you're just going to look them up on the table. There's no way to look at the front side of the periodic table and find out anything. If it says nitrate and you don't know what nitrate is and you don't remember, which you probably won't, all you have to do is flip your table over and look up nitrate. And you can see exactly what its formula and charge is, because that's really what we need, is we need to know formula and charge to find out what the formula of the ionic compound is going to be. Now, a couple of examples of polyatomic ions. Ammonium is the only cation that is a polyatomic ion. All of the rest of the cations that you see on the back of the periodic table are just a single atom losing electrons. But ammonium is a polyatomic cation. It's a nitrogen with 4 hydrogens bonded to it, and that collectively sticks together as a unit. And to become stable, that unit lost 1 electron, so it has a positive 1 charge. And this is the only cation that's not a metal. So when we talk about ionic compounds or metals and nonmetals, it's really an ionic compound is a metal or ammonium with nonmetals to form a ionic compound. Now, one of the things that we're going to recommend when you have polyatomic ions is that you always put them in brackets, because we're going to be using the charges and the number in the charge, +2 versus +3 versus +1, in order to find out our formulas. And that 4 there is going to cause a problem, because this is not a 4 positive. This is NH4 as a unit, and collectively that one thing has a positive 1 charge. So to make it easier and not mess with that 4, it's just going to be there. If you've got ammonium, it's NH4. What we recommend is that you write it in parentheses. So we make ammonium, when we copy it off the back of the periodic table, I'd write it as NH4 in parentheses with a plus outside of the parentheses. And that then reminds you that this unit has a positive 1 charge, and it's not a 4 plus charge. So you don't do something that you shouldn't be doing with the 4 that's there. Another example of a anion that we're going to see from time to time is the sulfate anion, and that's SO4 2-. So following the same principle, to keep it less confusing, and remember that's 1 unit with a 2- charge, we put it in parentheses. So we'd write SO4 in parentheses and then put the 2- outside of the parentheses. So those would be examples of what we call polyatomic ions. And there's a lot of ionic compounds that contain polyatomic ions, in particular on the anion side, because when you look at the back of the periodic table, on the right-hand column, the negative ions, there's a lot of different negative polyatomic ions. And you don't need to memorize them. All you need to do is look them up on the table. So keep your table handy for what we're doing in this semester. Now, the rule of thumb, and what we're going to use to figure out what the formula is going to be, is that overall compounds are always neutral. So molecular compounds are neutral, ionic compounds are neutral. But since ionic compounds are made up of charged ions, we need to find the ratio of cations and anions that actually gives us a neutral. And I showed you how we can move electrons to see what the formula is going to be. Well, it's a lot simpler than that. We don't really need to move electrons. All we really need to do is look at the charge to help us figure it out. But that's the key. We need to find out how many cations and anions we would need to get an overall charge of 0. So what would be the formula of sodium chloride table salt? Now, you've all seen and probably heard me say, if not other teachers in the past say, that sodium chloride is NaCl. How come it's NaCl? Well, it's based upon the charges of the ions present. Sodium is a +1 charge, so when you look up sodium on the back, it's Na+. Now, we could also look at the front of the table and see it's in the first column, so it's going to lose 1 electron. That's why it's a +1 charge. When it gets together with the chlorine anion chloride, you'll see on the back of the periodic table that's a Cl-. That's a -1 or 1-. And if you look at where it's at on the periodic table, you could also see that. It's in the 7th column, so if it gains 1, it looks like argon. That's why it forms a 1-. But honestly, if it's on the back of the periodic table, you don't really need to look at the front of the table to figure out what the charges are. You just look them up and copy them down. Now, if we have sodium chloride, we have to have at least 1 sodium and 1 chloride. And at this point, if our charge is overall 0, then that's all we have is 1 of each. And since sodium is a +1 and chloride is a -1, 1 of each would give me an overall charge of 0. So that's why sodium chloride's formula is NaCl. It only takes one cation of sodium with one anion of chlorine, called chloride, to make a stable neutral substance. So sodium chloride is always going to have the formula NaCl, 1:1. And that's really how we are going to end up using our charges. And there's a couple of different techniques or shortcuts we can use, but fundamentally that's all we're doing, is how many of each do we need to get it to add up to 0. Now let's look at one that's got a polyatomic ion in it and one that's got our multivalent, it's called, cations that can have more than one charge and be stable. Now, normally I would look up iron 3, but honestly, it's iron 3. Roman numeral 3 means it's a 3+. So I know my cation is going to be Fe3+. I didn't even really need to look that up. Now, sulfate, on the other hand, I'm probably going to need to look it up because I haven't seen enough of them, or you haven't, to probably know that whenever I see sulfate, it's going to be SO4 2-. And remember, we always write polyatomics in parentheses. So it's SO4 in parentheses with the 2- outside. Now we're going to do the same thing that we did with the sodium chloride. We're going to look at, we have to have at least one iron, and we have to have at least one sulfate. Now the problem is, last time we already were at 0. But if I have one of each, I've got an overall charge of +1. That can't be the formula. It can't be one iron with one sulfate. Well, at this point, I am short negatives, so that means I need another sulfate. So another sulfate comes in with its 2-, and that's going to give me more negatives. But my problem is, it's still not equal. Now I've got a -4 and a +3 total. So it's still not equal. But now I'm short cations. I'm short positive ions. So I throw in another iron, another Fe3+. So now it comes in, and now I've got a total charge of +6 and a total negative charge of -4. Still not equal, and now I'm short on the negative side. And at this point, it looks like this could go on forever. But notice, we are only 2 away. So when we add that next sulfate, now we have a +6 on the left, a -6 on the right, and that's going to add up to 0. So when we have iron 3 sulfate, there's only one formula that would lead to a stable neutral compound, and that's Fe2SO4 3. And you can see why it was convenient to have that parentheses. If I have 3 sulfates, I have to put the SO4 in parentheses anyway. So just always put your polyatomics in parentheses. Now, this is technically what we're going to do with all of them. We're going to look at and try and figure out how many cations and anions we need to get them to add up to 0. But there is a shortcut technique called crisscross reduce that you can use that makes this a whole lot easier. So what we're going to do is crisscross the charge values and write them as subscripts. Now, crisscross means we are crossing both sides. So that's going to be a very specific thing when I show you exactly what that means. And then once we've crisscrossed the charge values and written them in as subscripts, if we can reduce those two numbers, then we reduce it. So that's why I usually refer to this as crisscross reduce. So going back to the one we just saw a second ago, iron 3 sulfate, how would that work? Well, first you look up and you write down what the formulas are and their charges. And then what we're going to do is take the number in the charge spot, not the sign, just the numbers. So 3 plus is 3, 2 minus is 2. And we're going to crisscross those charge values. We're going to move the 3 over to the one side at the bottom. So that 3 is going to go with sulfate. And we're going to crisscross over the 2 to the iron. And now what we've got is Fe2SO4 3. You ask yourself, can you reduce it? No, 2 and 3 can't be reduced. So that's got to be our final formula. So iron 3 sulfate would equal Fe2SO4 3, just like we showed a second ago. So honestly, rather than just keep figuring out how many cations and anions and finally get to 0, it's easiest just to write them down and then crisscross reduce. Now, what would a reduced situation look like? So you see that? Well, let's say we have tin 4 oxide. Remember, Iv is a Roman numeral 4. That means we've got Sn with a 4+ charge. And it's with oxide. If you look up oxide on the back, it's O2-. And if we crisscross those values, the 4 goes down to a subscript in the O, and the 2 goes down to a subscript in the Sn. Well, 2 and 4, unlike 2 and 3, can be reduced. I can divide both of them by 2. So I'm going to reduce these then to a 1:2 ratio. And that can't be reduced. So that's going to be my formula. SnO2. 1 tin, 2 oxygens would lead to an overall neutral situation, because that would be a +4 -4, that equals 0. So crisscross reduce. You crisscross the numbers and then you reduce them. And don't forget, always put your polyatomics in parentheses. Now, the next thing we're going to end up looking at is naming ionic compounds. But before we get to that, we're going to practice finding formulas for a while. So that's in the next set of notes.